So the first session for today will be the Taste of Time award. So the goal of the award is to reward the paper which was most influential from 10 years ago. So for ICML 2008. So for those who were not there, which is a majority here, ICML was held nearby in Helsinki. There were like 5 times fewer papers and 10 times fewer participants. So this year the program chair decided to let the area chairs nominate some papers. And then the best paper committee, which took care of all the awards, was formed to reach a decision. And this year, this decision was quite simple for the Taste of Time award, and it goes to the paper by Ronan Colobert and Jason Weston, a unified architecture for natural language processing, deep neural networks, and with multitask learning. So quantitatively, this was by far the most nominated paper by area chairs, and it has a huge number of citations, 2,000 for, more than 2,000 for the ICML paper, and 3,000 for the subsequent JMLR paper. But most importantly, this was highly influential on our field because this was one of the first papers to use deep learning within natural language processing. So now Jason and Ronan will tell us all about it. So please welcome them with a round of applause. And I have some certificates. Okay, so I'll give it later. Okay.
Thanks.
Thank you.
Thanks a lot. Yes, thanks to all of you. So it's my pleasure today to be with Jason again.
And it's my pleasure to be with Renaud.
Yeah, so do you remember actually about this stuff? It's quite old, right?
I don't remember how many years ago exactly. And I can see the title there, but I'm not 100% sure of the content. Maybe we should look back at the old slides.
Yeah, let's dig a bit in the past. Yeah.
Seems like we had a little bit different style back then.
Yeah, but we were at NEC Labs at the time, right?
Yes, 10 years ago.
Oh,
I remember we were working at NEC Labs.
And now we are back together at Facebook, right? It's awesome.
It's nice.
So what was this paper about after all?
So I remember now. It looks like it was about a neural network architecture tried to define in a general way that could be applied to all kinds of NLP tasks.
Oh.
I think,
the
that
said,
kind of matches the title.
Unified architecture for natural language processing, and actually we even put the keyword deep neural nets, man.
Yeah.
Okay.
And we were training also on many kinds of tasks, and there's the multitask.
No, I remember actually. So the idea was you have this kind of unified neural net architecture. And what does it do? I mean, it takes actually words, pure text, and it can be words or subword units actually. And those words or subword units were converted into word embeddings, like vectors, things that the computer can actually understand.
Right. And then after learning after the word embeddings layer, there'd be subsequent layers, convolutional layers, like CNN layers, right? So that kind of came from the vision community in a way, and we kind of brought that into this kind of architecture for NLP.
Yeah, totally. But the problem is, how do you deal with variable sentence lengths, right? You had to deal with that. So what did we do about that? You remember?
I think, to make sure there was a fixed length vector for every word that we wanted to predict a tag for, we did a max over time.
Oh, yeah. Yeah.
And that could be seen as a kind of attention mechanism in a way, because it's going to select some relevant words for that tag, and you can actually visualize that and look at what it's doing.
Cool. So, and in fact, we were training, that together. Jointly, several tasks at the same time, right? Sharing actually part of the networks, and in particular sharing this lookup table, right? Yeah, I remember that now.
Right, yeah. We were training on these different NLP tasks, semantic role labeling, chunking, named entity recognition, part of speech tagging, all with the same architecture.
Yeah, but also this, language modeling task, actually, which was super important. We were training like on Wikipedia with the same kind of architecture, just to like train proper embeddings, actually.
So that unsupervised task was important because otherwise we were kind of overfitting on those tasks with a relatively small amount of data. So if you look back at the amount of sort of neural network papers that were kind of around then, if you look at, say, ACL in 2008, with papers with the title that contained, say, the word deep or the word neural, there wasn't that many, actually.
None. Yeah, none. But since then, actually, well, you know, there were progress. I mean, somehow deep learning like took over in the NLP community, and nowadays there is like even like up to 70% or more of the papers.
Yeah. It looks like that's increased a lot, say between 2012, 2017.
So what about like machine learning conferences actually?
So yeah, in ICML 2008. So back then, when the paper was introduced, there was say 4 papers with those keywords.
And 2 of them like were actually our own freaking paper, right?
One of them with Frederick Ruttler.
Yeah.
Yeah, but one of those is this paper actually.
Yeah.
Right. Oh, that's why we're here.
Yeah.
But if you look, say, this year ICML, then those 2 keywords, there's over 100 papers like that, and more that actually are about neural networks.
So let's try to understand a bit better, the setup at the time, right? And like, let's do a little, timeline to understand where we were at the time.
Okay, yeah. So this paper was in 2008.
Oh yeah, but actually the year before, we actually already published at ACL. Some paper on the same kind of, with the same kind of ideas, right? We didn't have the language model training, and it was only on semantic labeling, but we had everything else, right? I believe.
Right, yeah. It was definitely an improvement over that paper, particularly influenced by the work of Yoshua Bengio and co-authors who trained these nonlinear neural net language models in a paper in 2001.
Yeah, so the big difference with our paper is that they were not using these embeddings for other NLP tasks, right? That's what we brought, basically.
Right, they were just doing the unsupervised learning of those word embeddings, but we kind of integrated something like that into our 2008 paper, training also on the supervised tasks, and that's kind of what gave us a gain.
Actually, let's zoom a bit out in time, right?
Ooh, if we go all the way back to 1989?
Dinosaur time. So, yeah, actually, we were also quite influenced by, this ConvNet paper. We are kind of fan of that, right?
Yeah, Yann LeCun. So, so these convolutional neural networks for vision, that's kind of an idea that we try to take that kind of architecture and put it into NLP.
Yeah, actually, ConvNets were already quite used in computer vision, but also speech processing, right? But not,
Right, and biologically speaking, I mean, they can also be seen as plausible because they're probably like a dinosaur eye even has like a ConvNet in it.
I don't think there is any like fossilized CNNs known, right? But whatever.
Maybe not. But then why these ConvNets, which are pretty cool and they're used a lot nowadays, they weren't really used that much in the 90s as I recall. I was around. Oh, it's because of this paper in 1992. Bozycki on Vapnik, the SVMs.
The meteorite of CNNs.
Right. There was all these papers at that time, kind of like hand-engineered features applied then to a linear system like an SVM, and that was kind of big in NLP, but also, machine learning and vision as well.
Yeah, it's true, yeah. But then, for years, actually, it was the ice age for CNNs. Yeah.
It was. But yeah, so even up to, say, 2008, you could see the best paper at that ICML was about SVMs.
Yeah, actually, the best paper was like a good theoretical paper about SVMs. So let's go back a bit, like, focusing on our paper and things which are around. So actually, we had a follow-up of our paper like a few years after. It was a GMLR publication where we kind of polished the work we have done.
Right, yeah, we done a more thorough comparison with the better metrics on compared to existing NLP tasks, and also had some improvements in that paper.
Yeah, around that time there were also like AlexNet actually for for ImageNet, which came up in computer vision, right?
Right, that was a year after 2012, and
Yeah.
that was kind of the big moment when people kind of realized, oh, these neural nets really work for vision, and kind of neural nets really took off in not only vision, but other fields as well, I would say.
Yeah, indeed, yeah.
But, in our work, we kind of done these nonlinear word embeddings, and computers were pretty slow back then, so we were kind of also thinking, oh, maybe we should go back to a more linear system and try and train these fast word embeddings.
Yeah.
So like that way. So we had a paper in 2009, supervised semantic indexing.
Yeah, it's true. But I would say that like word embeddings really started to be really popular with like the Word2Vec paper, right? Much later in 2013, right? Because Word2Vec like proposed, a very nice linear algorithms, right? Which with like an efficient implementation, right? So I would say like the field started really to explode around that time, right?
Right, and then there was subsequently lots of word embedding papers, algorithms, and applications.
Even today, actually, right?
Even today,
Yeah.
but you get to the point today, actually, computers have got faster, and people are kind of more exploring like those nonlinear neural networks for word embeddings again. So like a method like Elmo, which is pretty recent, is kind of harks back in a way to, the Bengio paper of 2001 and kind of our work as well, 2008, in that they're doing those nonlinear embeddings and getting very good results.
Yeah, so after like word embeddings started to be really used, like the community came up with all sorts of improvements, right? For neural nets, like for example, sequence-to-sequence models based either like on recurrent nets or recursive nets, right?
Right, yeah, so many innovations, and it's really cool to see what's happening in the field. I mean, other things that have happened, like attention in machine translation was first introduced and then is used all over the place. Things like using bolting on a memory to neural networks. I mean, things like neural Turing machines and memory networks.
Yeah, and actually, even like it went even like up to our own products, right? In our own companies, right? Because like machine translation, for example, is based on this kind of techniques nowadays.
Right, so yeah, finally all these techniques can be used in real product, like something like FairSeek from Facebook is like a convolutional seek-to-seek method for translation summarization. And, so the CNNs used there, you could also link that to the CNNs used in our paper we're supposed to be talking about today.
Well, let's talk about it, actually.
Yeah, let's actually talk about it a little bit. So, as we were saying, at the time, there was this kind of way of doing things in NLP that you would have like a task, like part speech tagging, and you would just train, like you'd hand engineer a bunch of features, train that classifier, and then the output of that classifier you would use to build more features to another classifier for, say, parsing. So you build this cascade, and you might get errors from that, but it's not end-to-end.
Yeah, I think, Jason, you forgot to say something, like a disclaimer, right? I mean, this is like a null slide, right? Back from the ancient time.
Right, when we did things differently.
Yeah. And actually, the way we were selling our stuff compared to the rest of the people was to say, you don't need all these features. You can train in an end-to-end way. And so, for example, take whatever data you have, like an image, a piece of text, or whatever. You are going to embed it into like a vector space, and then you are going to pass that through a bunch of neural net layers, which are going to get a higher and higher abstraction of your input data. So that was the kind of things we were saying, and it was really new for the community.
Yeah, right. So that was kind of the dream of some neural network vision researchers you can see in this image.
Yeah.
But again, this was before AlexNet, so most people weren't really believing in that, even in vision. And certainly in NLP, no one was doing that. But so we were inspired by that to try and make this architecture for NLP.
Yeah, so the big picture in the end of our paper was, really this scheme which is like still used nowadays, where you have like a piece of input text that you feed, into a word vector embedding, right? I mean, that you transform into like word embeddings, and then those word embeddings are fed to a neural net architecture, whatever it is, and this may be, trained together with like an auxiliary task to have better embeddings.
Right. So. Yeah, so looking at those word embeddings, so so first we tried like just training on a supervised task, and there wasn't that much data for those tasks. And we found things like the word embedding of feline wasn't very well trained compared to, say, the word embedding of cat. And what we really would like is those vectors to both be well trained and probably be to kind of be similar to each other, right? So if you looked at the nearest neighbors of one, the other one would be close. So we wanted to try and train something like that. And one way to do that would be to use lots of unlabeled data.
Totally, lots of data. And actually, we set up a kind of language model task where we train an architecture which was similar to our, other neural net architecture. And the model was trained to understand, if like a piece of text would be actual English or not, right? So we would take like a piece of text in like the Wikipedia corpus and say to the model, look, I mean, this is like true piece of text. But then we would scramble a bit this piece of text and say, look, this is like, a fake English sentence. And the network was trained in this way.
Cool, yeah. So that way of doing things, taking like a window of words and then trying to predict the middle word, that's kind of something that other word embedding algorithms kind of used as well later on.
Yeah, and we trained that, massively. I mean, massively for the time, right?
Oh, how long did that take to train back then?
So the crazy thing is that we kind of forgot one experience on one server, I remember, right? And it actually trained for 2 months. And
2 months, that's crazy.
And that's the results that we show in the paper are actually, the results of this single experiment. Yeah.
And these are what the nearest neighbor of some words look like.
Yeah, it's
after
like
training.
random words picked in the dictionary, and underneath you see the rank of this word in a dictionary in frequency, and underneath the 10 neighbors basically in the embedding space. So it was working amazingly well. Yeah.
Cool. Yeah. So this is sort of things that people are used to seeing nowadays, but at the time there wasn't really any results like that with neural networks, as I recall.
Yeah.
So that's just the first layer, the word embedding layer. And then, as we said, the next thing that happens is we go through some convolutional layers, and then we need to do this max over time.
Yeah, totally. So the max over time is trying basically to find the best feature, the most relevant features at each time step for the label you want to predict, right now, basically. So, for example, this was not super well explained, unfortunately, in our paper, and we showed this graph in like a follow-up paper. But for example, for semantic relabeling, where you need to predict the label of one word according to basically a verb you chose beforehand. So here in the left graph, the verb is proposed, and the word you predict is report. You can see that the number of features which are chosen by the max procedure are mostly around the word of interest and the verb of interest. So it was a kind of dual attention.
Right. Cool. So how did all this work in actual experiments?
Oh yeah, we reported results in word array for all the experiments.
So we can see like 3 tasks here: part speech tagging, chunking, semantic role labeling, and this word error rate for either training alone or with the multitasking.
Totally, and like on parts of speech, we were basically state of the art.
Okay, but the multitasking doesn't help too much there, but I guess the numbers are already pretty low.
Yeah.
But on this chunking, they help a bit.
Slightly, yeah, but the best boost was obtained like on semantic role labeling. And here again, you have to remember, we are not cascading the task, right, as many other people were doing. The tasks are trained, jointly, and basically somehow the model learns like relevant features for one task and is able to transfer the knowledge, to the other task. So that was really the cool thing about that.
Neat.
And we had with that a very fast implementation, basically.
Cool. So it took a long time to train, but test time was fast.
Yeah, exactly.
So what did the NLP community think about this work?
I think it didn't land that well, right?
Oh, here's a website from the time, actually, and it seems that some people maybe just didn't really get the work.
Yeah.
Maybe it was just a little bit too different at the time.
I remember we were a bit shocked by that, but there is maybe like several reasons for that. One is indeed it was quite different, neural nets, end-to-end, no features. But the other thing is maybe we should have done a better job at comparing with others. The metrics we were using, were not totally proper for the NLP community.
Right, yeah, the metrics weren't completely right, and that's something we fixed in the journal paper, right? That took a couple of years to come out because of a long review cycle. Yeah. But in the end, we had a thorough comparison to existing work, and we also had some novelties in that paper
extra
too.
Stuff like the sequence learning, using like a kind of nonlinear CRF, basically, So we were training the neural nets through a CRF.
Cool. So maybe we should just conclude then.
Yeah, I think time is out. Yeah.
Okay.
Yeah, so I would say like in the past 10 years, we have seen actually a big paradigm shift in the NLP community, but also in the machine learning community in general, where we came from like feature engineering and we went to architecture engineering, right? So this brought some interesting novel algorithms. I mean novel architectures like which embarks like memory, for example, or like new sequence-to-sequence models, or new attention mechanisms, right?
Yeah, all that stuff's really cool, and I think there's still lots of work to do in those areas. But one question is those architectures that we have right now, are they actually enough to do those things that we want to do in the end? So Renaud and I have, a dream, maybe you as well, of like talking to our computer.
Yeah, we were saying that all the time at the time. I mean, we were quite geeks, yeah.
But we're still not not there yet, right? Yeah. And so, the things we can't do are actual dialogue, like the ability to, sort of learn language, perform in the environment, to be able to learn, while talking, interacting with this model, to be able to do some kind of reasoning.
Yeah. So in the end, the question is, I mean, the architecture that we have right now, are they enough, or do we need like a new paradigm shift? That we will see basically.
Yeah. We're excited to see the future. Yeah. Thank you.
Yeah. Thanks.
All right, so we have time for a few questions. So if you want to ask a question, please go to the microphones, which are in the middle of the aisles. No.
Can I grab this?
No question? Okay, so I have one. So with like actual computing power, how long would it take now to train the exact same model?
The Wikipedia one?
Yeah.
1 hour, not even.
Wow.
Yeah.
So, no questions? Okay, so let's thank the speaker again. Speaker.
Thank you.
Thanks.
And I have like one announcement. So there is a business meeting this afternoon at 6:15 in room K1. So if you want to know more about how ICML operates, both on for the reviewing and for like choosing locations, so please come at 6:15 in room K1.